Welcome to Lecture 6 for Lean for Scientists and Engineers. We are now on the last lecture of the first module, Logic and Proofs for Scientists and Engineers. And starting the next lecture, Lecture 7, which will be in 2 weeks, we will be getting into functional programming in Lean. So we are right here on the schedule, calculus-based proofs. Next week, we get into functional programming in Lean, where we'll be doing more about functions. We did functions last time. Today will be a bit more about functions and then delving into calculus-based proofs. A shout out to Tomas Scriven. He developed one of the tactics that we're featuring in today's lecture that makes certain parts of calculus-based proofs easier to do, which is a neat thing about Lean. All right, so today we're talking about we're going to recap lecture 5 and then talk about some more stuff that I think I missed discussing yesterday about functions and their types. And then touching on junk values, so we can revisit a thing that happens when we're working with calculus and Lean, and then work through a bunch of examples. We have a lot of problems in the lecture 6.lean file, which I posted to Zulip. So some recap. Once again, there's strategies to find tactics. Keep learning, keep practicing, consult lists, and as you do more proofs and inspect with VS Code mouse over tools, you will eventually get better at recognizing the patterns and figuring out what's going to work in which situation. For theorems, it's likewise. Keep practicing. You can also use MATLAB documentation and Moogle, lists of useful theorems, asking on Zulip as well. We're going to talk about SIMP question and ASOP question, some tactics that help you find theorems too, later in this lecture. And by now we've had several lectures where we've been talking about these logical symbols and or not implies if and only if exists and for all. We'll be touching on some of these again. And last time, we were also talking about what is the difference between a function from a programming perspective versus a math perspective. And we also talked about what this means from a physics or scientist's perspective as well, but you can check back on the last lecture to hear a lot more discussion on that idea. But the bottom line is, in a math perspective, a function maps values from a domain to a codomain. And this is a bit different from the programming perspective, which is more about you have a function, it takes an argument, it performs calculations, and it just produces an output. This is more of a mechanistic, step-by-step thing about what a function does. You know, what a program does is it performs these calculations and it does a thing. Okay, a function from a math perspective is about what it is. It is a mapping from a domain to a codomain, and that distinction between what a function does versus what a function is actually the basis for how we can do proofs about math objects and do proofs about function objects. So we discussed at length this square root function where it's not a problem to set this up in Python, but sometimes you'll get errors or unexpected behavior if you, for example, pass a negative number into this. But in Lean, we might have a function called real.square root, and from a math perspective, this is not always a function, because once you have a negative value, then if this is supposed to be a real number, if it is real to real, there's no part of the real domain that maps to the real codomain. Okay. If instead I did real to complex, then it is a function because there is a mapping from the real domain to the complex codomain. And this is another example that I wanted to just bring up to help illustrate something. So this is, I could have slid this into lecture 5, but here is another illustration of this. And this is another thing where it's not a function if you're looking at it from the math perspective. This is a type real to real to real. We'll share in just a few slides how to make sense of this type of function type, but everywhere in this domain, there's a solution. There's only one case, okay, when y is equal to 0, where this does not map to a place in the codomain. And that makes this, the mathematical sense of this, not a function. And if you do this in Python, it also sort of breaks that idea, because if you try to divide by 0, you'll get not a number coming out. Something that's invalid. Not a number is not in the domain of, it's not in the codomain. It's not something that should be a target of this, but there, nonetheless, it points there. It's just kind of invalid. So the Lean's solution, and many theorem provers, not just Lean, have this be the solution, where they say if y is equal to 0, then we are going to define a value in this real domain that satisfies this. And I've given this link before to this division by 0 in type theory frequently asked questions blog post from Kevin Buzzard, which is, I think, really helpful for coming to understand this phenomenon. Importantly, that this definition does not lead to any contradictions in the system. So it doesn't compromise the ability of the theorem prover to prove that some things are true and to fail to prove that other things are true as well, when they are false. So reminder of several number systems, because this ties into that place that the integers, for example, don't contain any fractions. The rational numbers don't contain pi. Complex numbers, the real numbers don't contain any of the numbers with an imaginary component, for example. And this understanding of what these number systems are is largely what's behind some of those unusual treatments of functions. And we have a question about, does this kind of definition mess up any kind of continuity in case we're trying to prove that? Excellent point. How do I explain this at the level that I want to handle in this course? I'll just say stay tuned. And after we talk about calculus, revisit this question or come back to it, because this totally comes up in questions of continuity and smoothness, differentiability, things like that. Right. And so we spent some time thinking about functions from a physics or science perspective, and looking at these and thinking, well, how do I come to understand these? And something that the following slide is something I wish I brought in, because it has to do with what is the type of a function that involves more than one variable. Temperature is a function of x and y, or a function of r and theta, or something like that. And the idea here is called currying. This is a computer science term that deals with what happens when functions compose with other functions, when you have one function calling another function. And so if you start with a simple function, f of x is equal to x squared, the type here is n to n, the natural numbers to the natural numbers, because x comes in as a natural number and it produces a natural number coming out, x squared. This is type n to n to n. And it's a little, exactly what does this mean? And every function that has multiple arguments can be transformed into a series of functions with single arguments. And the way you can see this happening is if you look at, in Lean, the definition of natural number multiplication, nat.mul, the type of this is natural numbers to natural numbers to natural numbers. And I put these parentheses in here just so you can see what gets evaluated first. Essentially what this is doing is you're saying, I am going to map a natural number to a function. Single argument, single output. In goes a natural number, out goes a function. If we would then pass in this nat.mul, if we pass in the first argument, now we've sort of eaten up this one by passing in the x, and now there is a function that has been output. So the type of nat.mul x is n to n. And this is, once again, a single input and a single output. So now I say nat.mul x is going to take a function, and we give it y, and the type output here is going to be of type n, or basically, the type of what happens when you multiply x by y. A reminder, in many other computer languages, you'll use parentheses to mark off. Even in this notation, parentheses are used to show what is going to be in a function, what is not. Because functions are just everywhere in Lean, the syntax is to simply use a space. If you have a space in between variables, Lean will assume that the first thing is a function operating on the second thing. And that is what it's seeing. It's seeing nat.mul x is going to be a function operating on y. That will help understand the calculus proofs that we bring up shortly. Okay. The other part of this, and this is related to that division by zero question, is these are called junk values. So for the natural numbers, 1 divided by 0 is defined as 0 instead of defined as not a number. But that one might seem bad, but this one seems even worse, right? 1 minus 2 is equal to 0. What is that? Well, basically, anytime you have natural number subtraction, and if it's x minus y and y is greater than x, then the result is going to be set to 0. Because coming back to the number systems, the natural numbers don't include negative numbers. So the point is we're trying to do a function from nat to nat. And you can't do nat to z. That's just not the same function. You could if you wanted nat to z. If you wanted your subtraction to have z, to have the integers be your output, but maybe that's not what you want. The idea is it's going to be nat subtraction, natural number subtraction, and we always need to have every value in the domain map to some value in the codomain. And that picture, once again, says, okay, well, we have a problem if, it would be called a partial function if there were some values of some combinations of x and y that didn't map to a natural number. So the way Lean and Koch and Isabelle and many other theorem provers handle this is by defining these junk values, and now you do have some value in the natural numbers, because 0 is in the natural numbers, and every single input maps to an output in the domain. Once you do that, it just makes things a lot easier to write proofs about things. And it's if you're curious about this, I encourage you to spend some time trying to set up a proof and see what you can accomplish to see if you can try to derive a contradiction from this. It's hard. You might think there's a way to do it, but in the end, like it's like, oh, okay, I can't end up getting 0 is equal to 1 or 2 is equal to 3 by subtracting things, as long as I'm doing everything, as long lean is going to prevent me from making bad moves and so on. So likewise, there's a real dot square root. The type is real to real. -5 is a real number, and you need a source, you need a location for the square root of that, and so this is set as a junk value equal to 0. So Rick is asking a question. Can you give an example of something that would be hard to do with a function whose domain is the real numbers with inf and negative inf? This is a good question. These are called the extended reals. I'll hop into, just in case I can find the answer real quick. I'm pretty sure extended reals is a type. And I will go look for it in the documentation, just to illustrate. Yes, ENN real is, well, that's the non-negative reals, is what Arshak is suggesting. Might be E real. E real? Yeah, E real. So we have E real is includes negative infinity and infinity. And it's a type. And you can go to the documentation and find out. I'm not sure how to read this. Oh, I guess it's the real numbers with top. Top is the highest number. So with top is going to be the highest number, and with bottom is the bottom number. And so this is that. And I haven't ever written a proof using this type, so I can't go into much more detail with this, but yeah, it's a thing. And if that was relevant for your work, well, I'll have a comment about limits and filters in a minute, but this touches in on that. But good question. So the other, I want to also make clear, there's a difference between a junk value and these kinds of results. So what is 4 divided by 3 equal to for natural numbers? It's equal to 1. What is 2 to the power of 1/2? It's equal to 1. What is the square root of 8? When it's nat square root, this is equal to 2. And if you check these by reflexivity, that's the RFL tactic, you can see that lean thinks all of this is just fine. That here I'm trying to prove that nat dot square root is equal to 2. I could change this to 3, and it's not correct. You can't just put any number in here. But nat dot 9 is equal to 3, 10 is equal to 3, 11 is equal to 3, 12 is equal to 3. We can go all the way up to 16 before it's equal to 4. It's sort of doing this rounding down situation. And that's because doing a square root on a number, or a power on a number, or a division on a number, and leaving a remainder when you're working with the natural numbers, mapping to a natural number type is going to lead to this sort of thing. So this is a behavior you need to watch out for, especially if you're trying to write, I believe, so one of the examples I showed in lecture 2, I believe, we had this long equation in physics, and we were doing to the power of 1/2. But here, 2 is a natural number and 1 is a natural number. So 1 divided by 2 is equal to 0. Okay, so 2 to the 0 is 1, and it's not necessarily what you're expecting it to be. So this is different from a junk value. A junk value is something set by the definition of what this function does when it's operating on certain types. This is, I call it weird, but it makes sense if you think about the number systems. And notice that the natural number is the type that's inferred here. I also put in the lecture6.lean file an example for currying, where we can see the type of nat.mol is nat to nat to nat. If I do nat.mol5, well, this itself is a function. And the type of nat.mol5 is n to n. And then finally, we do nat.mol5 2. This is going to be n. This is type n. It's a 10. All right. I'm also going to wait. Okay, and now we're about to talk about how the derivative is defined in lean. So do we have any questions about this before we move on? Good question about infinity, by the way. Yeah, because the real numbers technically exclude infinity and negative infinity. If you want those, you need the extended reals, the e-real type, or to include that extra thing. All right. Okay. So here is my slide explaining what deriv is. And you can see most of this information in the documentation or the mouse over looking at the definition of deriv. Also getting some of this language from the mathematics and lean textbook. So deriv, this whole thing, deriv f together, has type real to real. So this is a function that returns the derivative if it exists, and it returns 0 otherwise. So what you do is you end up providing the function f, and you tell it what you're taking the derivative of. That is going to be the first argument. You give it a real number, saying you give it something of a type real. Maybe that's going to be your x, so you're taking the derivative of x, okay? And you get a function, and you get a real number coming out. Whoops, I didn't finish that sentence. And you get something with type real out. Okay. So if the derivative of exists, and the language here we've seen exists now, so exists f prime, basically, if the derivative of exists, that means, so if there exists an f prime such that has deriv at. What is has deriv at? It is a function that simply answers the question, is there a deriv? That takes in the function f, which you provided, is looking for the existence of some f prime given the x that we're, assuming the second argument of this is there. Okay, so if that derivative exists, then we have this statement about limits, that evaluating f on x prime is equal to f evaluated on x plus a tiny change. So x prime minus x evaluated with the derivative of x plus some error, and x prime, as it converges to x, okay, we end up with this approaching 0, this disappearing. Okay, so that is if the derivative exists and we get the derivative back. And if you don't quite follow this, that's okay, because a lot of this stuff is new to scientists and engineers. This is about filters, and filters are a generalization of limits. And the topology chapter of Mathematics and Lean talks a lot more about those. And so we go to Mathematics and Lean. Oh, so Lean mostly doesn't do symbolic math? What do you mean by that question? Oh, Paul, could you be quieter? No, this is not doing actual values evaluating. This is very mathematical. I mean, it's very symbolic. We'll see in the examples that we get to that it is very symbolic, but the bottom line is the way this type is defined, sorry, I'm leaving this at the wrong screen, is this is doing an evaluation of a derivative at a point, okay, and it can generalize this, and in practice it does generalize this to the entire function if you write it up a certain way. But yeah, I guess, yeah, I'll wrap up this point that this maps R as an input to R as an output. But remember, that's just the type. Exactly. So it can be mapping. Importantly, this doesn't map a function to a function, which is how you might think of it. When I think of differentiation, exactly, I think of x squared. Okay, that's a function, and it might map to 2x, a different function. But that's not how they define it. And as you get into working with these things, it can be helpful to spend a lot of time looking carefully at all the types of different things that we set up, because this is how deriv is specified. Okay, well, so I was talking about mathematics and Lean. Let me give just a little more context. So I'm specifically, we sort of jumped into chapter 10 a little bit, but we're not hitting a lot of the context here. For the sake of time, we could have, for example, covered sets. And once you learn about sets and do some set theory, then you're set up to talk about topology, which is chapter 9. Topology is about limits, basically, the abstract study of limits in continuity. And we were discussing an earlier comment, do reals include the infinity and negative infinity? And that totally connects with this question of topology. Writing proofs with at bottom and at top, for example, type of things are related to topology and limits. But the level of specificity and in the precision that Lean needs to handle limits with is sort of beyond how scientists and engineers typically address this subject, which makes it a little bit more for you to learn, but all that is here, I think, but you do need to understand sets a bit before you get into chapter 9. So my recommendation, if you do want to get more in depth, is to look at chapter 4 and learn about sets, spend a day on that, then look at chapter 9 and spend a day or two on that, do these exercises, learn about filters, and after that you will have a better understanding of how some of the foundations behind differential calculus works. But I think what we put together today is a way for you to see how we can do proofs with calculus without necessarily being able to manage all of the these prerequisites that are built into lean, and lean is definitely leaning on them. So it's a very rigorous way of doing calculus, but lean is able to abstract away some of these more difficult parts into behind the scenes things. So we'll see how that goes. I don't think anybody's quite taught this content in this order before, so we'll see. Okay, last slide before we get into some examples. Oh, one more point though, because I was talking about junk values. The derivative, if the derivative does not exist, returns 0. So that's a junk value, and that's why I was talking about that. So again, this is a way that if I have a function that is not continuous, that here is a point on my function which doesn't have a derivative, the derivative doesn't exist, well, that means deriv f would, I mean, you can kind of think that's sort of like a not a number type scenario. There's something like, well, the derivative doesn't exist. So I'm at this point and I want to map to something, but that thing doesn't exist. So the solution is to put in 0 as your answer. And does that lead to some problems? Well, not really, because if you tried getting the derivative, well, it doesn't actually exist. So you won't be able to get it. But this function itself is going to return 0, but it also knows that the derivative itself doesn't exist. All right, and so here is some strategy or some preview of the things we're going to be looking at today. SIMP and ASOP are helpful tactics that find lemmas in MATLib. And if you leave the question mark off, they do the same thing, but they don't show you what lemmas were found. I generally recommend question mark because you can replace the result that they give you with, I mean, you can replace the query with the result they give you, and that is going to be just faster because you don't need to run the query and the result. And you only need to run the result itself. So we'll also talk about the show tactic, and we'll also show the fun prop tactic. So Misbah Malik is asking, would the derivative of infinity, what would that be? So what would the derivative of infinity be? And my question is, well, it depends on the function that you're looking at. See, I'm imagining a function that goes up to some value and levels off. And if it levels off and ends up being flat, then maybe out at infinity, the derivative is going to be equal to 0 because it's flat. And right, and Manu is bringing up a very curious point, very important and interesting thing. Like a derivative of a constant function is always 0. So I wish they used something other than 0 as a return value if the derivative didn't exist. And I hear you. It's just how the theorem provers are constructed. What other return value should we use? So again, we're thinking it's going to be the type is real to real. You're suggesting some doesn't exist type or something like that. Well, that's a trouble. That won't actually work as a junk value for this because some kind of doesn't exist type or another number doesn't exist in the, that's not part of the real numbers. That's not a member of the reals. If I picked a value 1 as my junk value, maybe the derivative of the of a function whose derivative doesn't exist, I could set that equal to 1. And I'm not so familiar with the ins and outs of this that I can't really think through that counterfactual situation of like, how that might be harder or easier than the junk value of 0 versus 1. And but what I suggest is revisiting that blog post about, let me go find my, let me go, that divide by 0 blog post. Posted the link before. We have that here in the slides, the division by 0 and type theory. Revisit that, keep thinking about that, and bring your questions to Zula. That the mathematicians who know more about this than I do have been wrestling with this and thinking about this and are able to think through those things of like, well, okay, well, would actually a value of 1 be a better thing than a value of 0, or would -1? What would be the consequences of setting a different kind of thing to 0? Because there are cases where I think you need to set up your proof in order to negotiate around that reality. Because maybe I'm trying to do a proof about this, the derivative of my functional being equal to 0. Maybe I want, when is the derivative equal to 0? Well, at the maximum or the minimum, right? Well, if that's the case, and somewhere in my function I also have a discontinuity, then, well, the derivative there is equal to 0 as well. So you just need to be aware of that and work out your proof, understanding that this particular function might have more than one 0 with different properties. The derivative exists at the local minimum, local maximum, and the derivative doesn't exist at the discontinuity. So there is a difference between those. They're not the same thing. But the mathematicians, and it's not just the developers of Lean. Back when Koch and Isabelle were built in the 1980s, people were putting these kinds of things into theorem proving systems. And there are some theorem provers that make different choices than this. And if you really want to get into that, you can go and study those things for yourself and come to figure out maybe some of the differences between these systems, as well as just ask people, because there are people on Zulip who are familiar with multiple kinds of theorem proving systems, and they understand the nuanced differences between something built with dependent type theory like Lean versus simple type theory, or set theory even instead of type theory, things like that. All right, and we have a question about antiderivatives or integrals. I'm just going to say, in this course, antiderivatives are outside of the scope. But if you want to dig into that, there's chapter 11 in Mathematics and Lean. And once again, it's a little unfortunate, but the calculus 1 and 2 and 3 that we typically learn in college don't actually really introduce the foundations behind this stuff. And so integration actually connects to measure theory, which is something you've probably never heard of, but that is an extension of topology. And that gets a bit more difficult. But it's there, and it's there to learn. We nonetheless will be doing differentiation for our case today. All right. And let's get to Lean. Okay, so here's where we were. Oh, I'm going to zoom in a little. And thanks to Colin Jones for all of these examples. He's the student in the Adams lab who's been working with proofs in Lean for a while and helped come up with these examples of derivatives using Lean. And so the first lesson is that simple goals like these can be solved using simp ? Or ASOP ? And let's just show you what that looks like. I'm going to show you the first two of these. If you enter in simp ? You look over at the info view and it has suggestions. That's what the simp ? is doing. And you can simply click on this link, apply suggestion, and it's going to change out this code with the suggestion simp only deriv const prime, and example is proved. Isn't that great? It's pretty clean. We can do the second one. We could write an ASOP ? and it has this suggestion, simp all only, and it puts 1, 2, 3, 4, 5, 6, 7 different theorems in here. We can just click it, and there it is. We can do simp ? as well. It's suggesting the same 6 theorems and so forth. And we've proven this one too. So these are simple goals. Now let's unpack how each of these things is stated. And so I'm going to move slowly and put my cursor intentionally in some different places so you can see what the different types are. And so the first thing is putting the cursor over deriv. And this is defining this. You see the documentation, which is the derivative of f at the point x if it exists. It's 0 otherwise. If the derivative exists, and it illustrates this, has deriv at functions where x prime converges to x. So this is the documentation of this. And let me feel like hopping over to mathlib. Let's go to deriv so you can see where this is coming from. So here is deriv in the mathlib documentation, and has deriv at is a function. Let's look at that thing, okay? This is has deriv at. It simply returns f has the derivative f prime at the point x. And if we come over and look at the source, you can see that this is simply, this is being defined, it has these inputs to the function. It's being defined as has deriv at filter with ff prime x. This squiggly n is a set theory notation that you'll learn about when you get into filters, and then x. And so this is all I'm going to show you about this. If you actually want to understand how this is working, what it's doing under the hood, then go and read about topology. But for now, all you need to know or think about is these ideas. If you are working with some function that has some weird kind of behavior, like it is continuous but not differentiable, differentiable but not continuous, or I don't think the second one counts. But like if you're dealing with some exotic kinds of functions, then think about go and learning more behind the scenes things. But if you're dealing with relatively common functions which have proofs written about them already, then you should be good with just working with these higher level things. Okay. So that's deriv. This is the case that's a little easier to unpack. So if I put my cursor here, right in the middle, you see this whole thing is a function, r to r. Putting my cursor at this power mark, this is just a real number. So what this is doing, and I mentioned this last time, the keyword fun turns an expression into a function. So we are taking an expression, x squared, and we're turning it into a function and doing it in an inline sense. So it's just happening automatically right here inside of the example. So this is the function, f of x is equal to x squared, okay? the derivative of that function with x as the argument is equal to 2 times x. And so 2 times x is the real. And that is how we get real to real happening. So the output of deriv fx is equal to a real number, and that real number here is 2x. So I'm just going to come back now that we've unpacked all of that. I'm going to show this final point. The deriv maps a function and a real to a real. A function and a real to a real. So that's this function, first argument, and a real, second argument, to a real. So this last thing is an expression again. And then I put my cursor here and I have my goal, which is basically stating the front end side of it. And it closes the goal all in one shot, essentially by saying, I'm going to perform simplification using the lemmas tagged here. Simp only, so simp itself has a bunch of lemmas attached to it. And these are lemmas that the people developing Lean and simp, so forth, have said, in general, I want simp to have access to a whole bunch of stuff. Simp only says, forget all of the default lemmas that are attached to simp and only attach the lemmas that I'm following here. And so there's 6 lemmas that are attached here, and they mean things like a times 1 is equal to a to the power of 1 is equal to a. The derivative of a function x is equal to, well, let's see, how do I state this? This is the identity of the derivative. The derivative of f of x is equal to a function x implies 1. Well, it's just a trivial identity kind of relationship for differentiation. And I'm going to talk about casting in a little bit later, I think, when we have a different example. And this one is differentiable at. So this is bringing in, someone has a lemma showing that f of x, when I have a function of f of x, being when of x, this is differentiable at all values of x. So that's unpacking this example in all these different little parts. That's one of the neat things to do is if you can close a goal, and maybe you're sitting here and I don't know how to do this, but you can close it with simp question mark. Well, after you have the proof, you can go and learn more about what exactly happened and what kinds of theorems did Lean go and draw from in order to make this proof. Here's another one. This one is just the derivative of a constant value. The derivative of c with respect to x is equal to 0. And this one's kind of tricky because I might say, well, I have a function of x and that's equal to c, but x is not actually used. So if I put x in here, we get an underscore and it says unused variable x. We actually, if I open up the messages, we will get a warning here, unused variable x. You don't actually need to put this in here because it could be any kind of variable. It's not using that information because c itself is not a function of x. So putting an underscore here is the canonical way of removing that unused variable. Lean will figure out what this placeholder term should be as it compiles this code and works out whether it type checks or not. So sometimes Lean wants you to put things in here so it doesn't have these dummy variables hanging around. This is cleaner. You're saying, I know that the variable I'm putting here doesn't matter. as opposed to if you're putting X here, it doesn't matter, but you're maybe not understanding that. So they want you to put an underscore here to take that warning away. But either one actually works in closing the goal of the code. This only needed one lemma because look at that. I mean, it's really, really similar to the statement that we're looking at. So it's just saying you can simplify this by getting information about this lemma and just simplifying it, because that's all that you need. This is a really simple one, and it's already in MATLAB, basically. All right, and if you're just tuning in while I talk and talk and talk, you might have come up with the solutions for the rest of these. All of these, you're able to essentially close that goal by performing simp question mark or ASOP question mark to search through the MATLAB library and figure out which theorems are capable of being used with simp in order to close the goal. The reason this works is because people before us have done the tedious work of proving these rigorously and then adding them to MATLAB. What is the difference between ASOP and simp? Good question. I'm not quite sure myself, but I have an idea of a place we can go to look up that answer, because to get a little more insight into that. Nope, not what I'm looking for. Get me the Safari. Okay. I want so I shared this Lean Force spellbook tactics, and simp question mark is for simplifying the goal by combining some standard equalities and equivalences. It's weaker. Simp is weaker. It doesn't do as much work as ASOP does. ASOP is fancier. I think ASOP may involve I'm forgetting now. Oh, you know what we can do is we can look at is it in MATLAB? We can look up the documentation. ASOP. There's a lot about ASOP. Let's hop into one of these. ASOP is automated extensible search for obvious proofs. And here, I will just copy this and share it in the chat. It is similar to simp, and it builds a search tree, applying rules recursively to the subrules, and does a search. So you can read all about this type of automation tactic stuff. There's a paper about it, which was published in December 2022. and you can read all about how ASAP works. But it's like a search algorithm and optimization algorithm. I earlier used the analogy, finding proofs is like searching through a maze. I mentioned this in lecture 1, I believe. Let me go find that. Or maybe I don't quite recall where that was, but finding proofs is like, it's like a maze. And sometimes you need to find your way through the maze. Sometimes you can simply give it the solution to the maze, and Lean is going to check the path that it goes. But it's a lot harder to search through the maze and find a path that works than it is to prove that an existing path is going to work. Um, okay. And so that's a bunch of examples that are all relatively easy to just search for. And that's what simplification is doing. It's applying these different tactics. And you could go and find these tactics on your own, and you may have to. If simp doesn't work, then sometimes you need to do more effort into tidying these things up and figuring that out. And so ASOP is, I don't think ASOP is more efficient. I think simp is more efficient, but less capable. But I'm not sure. If you're really interested in those, I recommend reading the primary literature on that. Okay, so here's an example. I have 1 over x, and I want to find the derivative is equal to negative 1 over x squared. So let's do simp. Oh, it didn't work. Bummer. So we do this step, and I say, okay, now I have simplified it. I've taken the derivative. I just have negative x squared to the power of negative 1, so the inverse of negative x squared, and I need to show that this is equal to negative 1 divided by x squared. So that is me making progress on this, but I'm not done yet. I have an unsolved goal. The derivative is gone. Okay, so I've made some progress, but it looks like I can't just do this. So I'm just curious. I know this proof can be solved by applying an additional tactic, that one that we've learned in class before. Does anybody have any suggestions? We have a suggestion of trying ring. Ring does it. So no goals. Great suggestion, Rick. Thank you. Again, we sort of think of or remember ring as being algebraic manipulation, and that's all we need to do here. We need to take an inverse of this and show that these two things are equal. This does involve symbols. So, I have ring as a variable. I won't be able to use norm num here. That one didn't make progress on this. So ring closes the goal. And but you can see how simp was helpful. Simp was helpful to look at the derivative and make the actual derivative go away, but it didn't actually finish solving the goal. So here's another one. And this time, if I try simp, we have these suggestions. And okay, made it a long ways, but now we have x squared is equal to x squared. Well, that's pretty straightforward. How should I finish this up? Any suggestions? Ooh, yes, we have 2 suggestions. All right. Uh-oh. Reflect isn't working. Can we try ring? Oh, ring isn't working either. Uh-oh. Do I need to do this? Um, I think, comma, reflect. There we go. I just had to split this onto the next line. So we have the chain of tactics following, excuse me. All right, so that did work. Reflect worked as we were expecting. Reflexivity would be the preferred tactic, I think, here, because this is simpler than ring. And more fundamental. But ring solves it too. Oh, does it? It does not. Oh. The reason it didn't close automatically, by the way, and it actually ring can't solve this. Ring doesn't make progress on this. Look at this. We are trying to show that x squared is equal to x squared, but the 2 is an integer on the right-hand side, and the 2 is a natural number on the left-hand side. That's why simp wasn't able to make it go automatically on its own. Reflexivity is able to show this, and I'm not quite sure about exactly how it's doing, but it works. It's able to figure that out. So I have from Colin Jones a different solution to this one. And this is why it's saying types are a little bit of a difficulty here. Because after doing some of these things, it changes the type of the exponent from an integer into a natural number. And yeah, maybe reflect as typecasting. I bet it does. I mean, it can't succeed unless it's doing that. So so here's one solution to this. Oops, copy. Here is another solution to this. And my goal is I have here I'll show the whole solution and then we'll unpack it first. So we're going to do a rewrite and we are going to use this show tactic. And so I referred to in the slides, the show is kind of like the have tactic, but it does it introduces a new premise in line. And what we're going to do is we're going to show that negative x to the power of -2 with type z, with type integer, is equal to -1 of type integer times x to the power of -2 of type integer. So see what we've done? We've just said negative x is equal to -1 times x. Okay, and this is a statement that we know by ring. So if I do this, okay, it goes and replaces an implicit -1 in front of this x with a -1 of type z here. And Arshak is suggesting typecasting. We haven't explicitly talked about that in class today, and I was Again, I'm short on time in prepping this batch of lectures, but I really would have liked to come up with an explicit standalone example where you can show typecasting. But that's this little up arrow that appears when we do this. You can see this up arrow. It says int cast. Okay, we're saying if I have an integer, okay, if I have an integer that's equal to -1, I can cast this into the real numbers. It says up x represents a coercion, which converts x of type alpha to type beta. So using type classes to resolve a suitable conversion formula. So there's some vocabs that we didn't address quite yet, but I'll take a minute to talk about those now, with the benefit of having my slides. Okay, so coming back to these natural numbers. This is possible because every natural number is included in the integers. So if I have a natural number, call it number 3, I can cast it into the integers and say, now you have a type integer. You used to be type natural, now you have type integer. You can also cast into the rationals, the reals, the complex numbers, etc., because of the function of type classes. Okay, that was another word that showed up here in the documentation. I'm putting this. It's using type classes. So this is how Lean can organize different types. Like some types subsume other types. The complex numbers include all of the real numbers. The real numbers include all the rationals. The rationals include all the integers. So we can do this. It's called a coercion of moving one type from the smaller class into type, from the smaller type into the larger type, and that's organized through type classes, which is, again, technical stuff we're not going to get into, but if you but it's a way to understand what's happening and how that's all working. Okay, so that does one of these casts. There's another simplification to do as well. We can do a rewrite. So that -2z is equal to -1 minus 1 by ring. And this one replaces the -2 here with a -1 minus 1. And by doing this little adjustment inside of this derivative function, that sets us up to apply a particular function, a particular theorem from MATLAB, which is deriv z power. And that one is this one is a very generic one. You may think of it as, so when x goes to the power of m, then this is equal to m times x to the power of m minus 1. So I'll give you a minute to stare at that. Remember, this is sort of the generic differentiation of monomials, essentially. So if I have x to the 3, that's going to be 3 times x to the 2. X to the -1 is -1 times x to the -2. And this is a MATLAB theorem. We wanted to use it, so we had to do some adjustments of this in order to put it in the form that this theorem can take it. Do we need both of these? Let me just check. Yeah, no, we need both of these. So we can't actually use this until we've done that rearrangement. Oh, we're not done yet? Oh, I thought we were done. No, it says no goals. Yeah, we are done. Okay, yeah, we are good. Do we need this one? I want to just check again. Well, actually, is it figuring it all out? No, it doesn't. It doesn't work with all of it, but technically, okay, I guess so. Colin's solution technically doesn't need the second one. We only need the first one, the casting of that. So that's actually a little simpler example than the answer key that I have. All right. So the others here are variations on that theme. We can try a simp question mark to break this down and make progress on the goal. Oh, but this one didn't even make progress on the goal. Not really. No. So okay, that's not working. For this case, we do need to manually change some of these things and apply that. So here we are going to rewrite, and we're going to show that -3 with type Z is equal to -2 minus 1 by ring. This has set up the goal to be -m minus 1. So we're ready to go. And we can apply the derivative of Z power, which is in the shape it needs to be to get into no goals. Just want to check. Yeah. Deriv Z power is able to take in a hint too, which leaves the type of this even simpler, but we don't technically need it to close the goal in these cases. All right. So moving into this one, let me make, oh, I better keep watching the time here. Here we have yet another one, but this one includes a constraint that x is not equal to 0. And oh no, I'll quickly walk through this one and then we'll move on to the chain rule things. I want to make give us time to do one more. So the Colin's suggestion for this is we first do a show that -3 of Z is equal to -2 minus 1 by ring. That sets us up I'm working with real numbers. Okay, excuse me. The difference between this one and the previous one is setting Z, the number here is type Z versus type real. And so if this is type real, we can set this up and in this case, we don't have a deriv Z power object. We want to, can I hit it from simp right now? Simp only. Nope, it didn't finish it. Didn't make progress. ASOP. ASOP closes this. Okay, so here we can rearrange a bit, and that helps us make progress on the goal by doing a little bit of an adjustment to make it fit better into the cleaning up of into making the powers work out. And then we can use ASOP in this case. So remember, I just tried it with simp. Simp didn't do it. ASOP does. And we need some of these things like A does not equal B. Some, different kinds of proofs like this. And we need differentiable at and these. So I will leave this one as an exercise for you to work out on your own. And we're going to move on to the chain rule. Not the chain rule, the product rule. Okay. So the rest of the examples, before we get to a physics example, is the product rule. So how do I do differentiation of u times v prime? Okay. Well, this, as you may remember from calculus 1, we can do u prime times v plus u times v prime. And in lean, we can access this with a rewrite and this theorem from MATLAB. And this is going to be creating 3 goals for us. We need to prove that this calculation above is correct, but then it also creates extra goals. We need to prove that u prime and v prime are both differentiable, which is annoying, right? But that's what makes lean rigorous, is we end up creating all of these goals and we need to close all of them before we're absolutely certain that we're correct. Because imagine, well, I mean, I don't have any counterexamples in my head, but it's quite possible maybe that one of these functions themselves might not be differentiable, but perhaps the whole thing is, but the decomposition of them isn't. I don't have a counterexample in my head, but that might exist. And if you're not able to prove that one of these things is differentiable, then you're not allowed to do this product rule step. So we are looking at some trigonometric functions. We have x times sine of x. What is the derivative of this? Well, first we do the derivative of x with respect to x. Then we have sine x, so that's where the x goes away. And we have x times the derivative of sine of x, which is cosine of x. So that's how we're ending up with this answer now. How do we prove that it is true? Well, after doing this, you can see we formed 3 goals. And thank you, Manu. Yes, there's a small correction to my slide. Let me pull the slide back. Yes, prove that u is differentiable and v is differentiable. Yes, thank you. I mean, that's one of the nice things is you can make errors in PowerPoint slides all day long. PowerPoint is never going to tell you make mistakes. Lean, you make a little mistake like that in Lean, well, Lean will tell you, and you'll have to get it straight. So we have 3 goals, and how we're going to dig into this is we use this center dot. You can see center dot is going to be a tactic that focuses the main goal. It focuses on one of these goals at a time. So after this happens, you can see now I only have 1 goal. After invoking this, we're going to deal with this goal first. This is my point. We have the center dot character. You can access this with a slash dot or slash center dot. Notice that this is different from C dot. C dot is technically a different thing. Watch out for the typos around that. Okay. Oh, yeah, I'm teaching class right now. You sure had a short nap. Okay. The toddler has waken up and is saying hello to y'all. Okay. All right. Okay. And so, how do we close this first goal? The first goal is saying I need to do the calculus of this. X times sine of x plus x times the derivative of sine of x is equal to sine of x plus x times cosine of x. So that's my first goal. Any ideas? How do you think I should close this goal? ASOP, always worth a try. Let's try ASOP, question mark. Try this, simp only. Here we go. Look at that. We did it. So ASOP works. Might as well try simp while we're at it. Can simp do it too? Looks like simp works as well. How about this second goal? Okay, so the second goal, how do I prove that when I have x as a function, and x is a real number, how do I prove that this is differentiable? So this is why I mentioned this tactic, fun prop, before, because this tactic didn't exist actually until May of this year, or maybe a little earlier, but Tomas Scriven has been working on this to make doing calculus easier in Lean. And fun prop is a very handy tactic that closes this goal. We'll talk about fun prop for a minute. Where is my MathLib library again? All right, let's get up the MathLib library and open up fun prop. Oh, I have this open. Is it here? Fun prop. Here it is, funprop.lean. And this is a test explaining how funprop.lean works. And if you're curious, again, you can on your own time look more into it. But the main idea is that the desired function property is marked with the funprop attribute. So this is an example with measurable, and that's going to be connected to measure theory, which isn't exactly what we're looking for, but it also has tags for continuity, for differentiability, other things like that. And the idea is you would find very common functions, and in our case, coming back to the code, the very common function is x. A real number, just some variable being a real number, that is differentiable at all values. So this function has now been tagged with differentiable, and you just need to run funprop, and it goes finds that tag and says, you're differentiable, since my goal was proving differentiability. We also want differentiable at sine of x. If we try funprop, this one doesn't quite work. It's unable to do that. Actually, it's suggesting this. I never tried this. No, that wasn't able to do it either. But this one is the sine function is differentiable, and we know that because it exists in MathLib. Let me go and see if we can quickly search it up in the library. Differentiable at, okay, and now we have a whole bunch of functions, power, inverse, constant, apply, sum. We're looking at differentiable at dot sine. Okay, so this is a theorem, and we want to know that the function for a real valued sine function, okay, is differentiable for all real numbers. That's what this talks about. So we're just going to apply this theorem, apply differentiable at sine. In fact, this goal is exactly the same goal as that theorem, so we can just go and use it as exact. differentiable at sign is exactly what we're looking for. This closes the goal. Can I do dot sign? Can I do apply this? No? Oh, it doesn't know what this is. I spelled it right the first time. I'm unclear why the underscore is in there. Differentiable at underscore sign. Oh, this is the one. We actually found this one. Okay, so this is it's slightly different. Okay. Can I use apply here as well? I can use apply here as well. You can use apply or you can use exact in this case. Okay, so there's our first chain rule example. Now we have another example. This one is x squared times cosine of x. So let's do the rewrite. We get 3 goals. What should we do for our first goal? Any suggestions for the first goal? Got a suggestion. Use ASOP for all of them. All right. All right. Whoop. Oh, we lost our lid on the thing here. Okay. Well, ASOP actually didn't even work on the first goal. Not all the way. We have 2 times x times cosine x plus this. Okay, but it's any suggestions? How should we keep going? Is there a way to continue? Something else to try? Add ring. There we go. Now we're good. Yes. So you're starting to figure out at least one way to approach these things, but it's not just entirely random. Like we made progress on this by going and finding all these theorems from MathLib that help us to simplify this and make the derivative go away. We end up with a goal that is just algebraic rearrangement, and so we can hit it with ring, and that works for us. Oh, this one, oh, I lost this one. Apply this. I guess we didn't end up needing this. Excuse me. ASOP had 2 goals. I want to spend a minute. So, well, ASOP actually did close this goal all on its own. I just wasn't paying attention to this apply reflexivity. Reflexivity, this tactic was working kind of like ring as well. And we got no goals after this first one. So here we now only have 2 goals left. So we could have just used ASOP and used their solution. I'm fine with hitting this with ring as well. I bet this, well, I'm not sure. So either one of those works. But shall we try continue with this? Well, ASOP. Can we hit it with ASOP? We can hit ASOP on here too. All right, we're doing well. And ASOP, this ASOP didn't work. It says try this. Sorry. Well, that's not a real solution. Simp question mark? Did simp question mark? Made no progress, right? So that's not working. I'll also mention we don't need all of this either. We can also hit this second goal with fun prop. By the way, we're all cleared out. Can we do fun prop for this one? Nope. That one's not working. So in this case, again, what is our goal? We're trying to prove that differentiable at cosine of x. So we can go and get a theorem that matches this goal. Differentiable at sine worked for this one. Now we want the parallel one for differentiable at cosine is going to close out our goal. And now we're good. We can do exact as well as apply. I think exact is more efficient. I don't know, actually. Apply is more generic than exact. Exact only works when they exactly match. Okay. So one more before we get to a physics example, which I'll give you some homework. Okay. You should be able to do this one on your own. And if you are struggling with that, then just bring your questions to Zulip after class and we'll help you. Okay. Now we are on to the last little message about all of this, which is really going to segue into the second module of the course. All of the above things are just little proofs about a function which is defined in line. So this function only exists in the context of this example. It's not being used anywhere else. We want to be able to write proofs about functions defined outside the theorem. Our big picture goal for this course is to equip you to write proofs about software, proofs about programs. And if I define a function, then I want to be able to say, well, what properties does this function have? How does this function relate to other functions? And so here is a simple example, and this is one we brought up in lecture 1, where I have the force as a function of position. I've defined x the equilibrium distance. Here, I have a picture. This is from lecture 1. Okay, this is the mass on a spring for example. On these slides, I took out the word non-computable because in lecture 1, I didn't want to get into those details, but we've talked about non-computable now. That is elaborated on last time in lecture 5. But basically, we have x and k as real numbers, and this is the force and the energy of a mass on a spring. So the example we have in class, and then we have a theorem, okay, is about the force being the derivative of energy. So this one is going to be a little bit different. We have a different formulation. We have one more variable, actually. We have the equilibrium distance. So it's not necessarily putting the origin at the equilibrium distance. It's just wherever we want it to be. This is going to be a harmonic oscillator. And the force is a function of x. And if I put my cursor over force, you can see the type that it has. K, xeq, and x are all real numbers, and it maps those to a real number. So, we could do a check on force. Here is the type. R to R to R to R. There we go. That's the biggest one we've done so far. But this is what it looks like. Again, this comes back to the currying that I was talking about earlier in class. We have a function of 3 variables, which is being outputting a real number, and you can interpret it as a series of 3 composed functions that output a real number. Okay. So the thing that's different this time that we need to do is we need to bring these functions into our example statement. I could also name this a theorem. The only difference between example and theorem is a theorem takes a name. So I could say force derive energy could be the name of my theorem, for example. I'm just going to call it example for simplicity, but the first thing we need to do is we need to bring in our definitions of energy and force. So who knows a tactic I can use for substituting in the definition of a thing in for the name of the thing, replacing the name of it with a definition. Exactly, good. Thank you. It is dsimp. So how do I do it? Dsimp force. All right. And we have replaced the force part of this with that. Do we do dsimp of energy? Let's try it. Dsimp of energy. Oh, it's not working. Dsimp made no progress. Well, that's because energy is embedded inside of this deriv. It's not able to do that. And I really want to bring up this little thing. We have a question about rewrite, okay, but I'm going to hone in on the key thing to be following here. Deriv does not map a function to a function. It does not map an expression to an expression. It maps a function and a real number to a real number. It maps a function and a real to an expression. Dsimp is taking a function for force and it's replacing that whole function and it's ending up with an expression out here. If I look at this goal and I get my cursor over the whole thing, you can see the type of this is a real. I don't want this to be a function on the right-hand side. I want this to be an expression. So dsimp works. I want that to be the case. What I want to be inside of this, energy k x eq, is a real to real. I need this to be a real to real. Otherwise, deriv isn't going to be type checking. This needs to be a real to real. So energy x k eq is what I need this to be. And I can't quite use a dsimp energy here. How about a rewrite? Urja is suggesting a rewrite. Well, yes, we want to do a rewrite for this. And we could do show with an inline function definition for this purpose. I'm going to do it with have, just to make it a little bit more explicit. Have h. That way we have a name for this particular hypothesis. Right after this, though, I'll try to do it with show, and we can see. So what I'm going to do is I'm going to show that energy k x eq is equal to a function object x to r I'm going to take the right-hand side here and just paste this here. Okay, so I'm trying to turn energy KEQ into something of this kind of form. Both of these are of type R to R. And with this, I can do by reflect. And now we have an additional hypothesis in here, which we can use in a rewrite. Rewrite H. And now I have something that's going to be looking like the examples we were seeing before. So we're making progress here. Here, I'm going to break this out. We could also, if I copied all of this and I put it inside of the rewrite, then I think I could do it with show. Let me see. Oh, I don't need the colon equals, I just need the by. Ah, yes. So the inline solution works as well. This would take, if you're not going to be using this again, I think this style is preferred because it takes up one line of code is just as reasonable, I think, instead of 2 lines. And we don't introduce a hypothesis that stays in the context of the problem for later on. So I think this is the preferred way to do it. But both of these styles of it takes us to the same place of the solution. All right, I think I'll just keep moving forward with this one. All right, so now what should I do? I want to show that k over 2 times x minus xeq squared, the derivative of that with respect to x is equal to this thing. ASAP. ASAP we go. All right. Oh my. Look at all that. Okay. Although we hit a sorry. But did it make progress? Looks to me like it made progress. The derivative is gone. Now what do we do? Ring. We got the pattern figured out here. There we go. No goals. So we did it. Now this, oh my goodness. This is sure using a lot of theorems. Do we need all of them? Can I delete this one? Yes, I can. So that's a thing you can try doing. ASAP ended up finding things that are not needed. It still is able to get to no goals, and I deleted one of these. Do I need sub 0? Nope. Do I need mol 1? Nope. So you could use this sort of ablation to remove tactics one by one after you've found a solution in order to, as long as you don't as long as you don't break the goal. Okay, looks like, oh, we broke it. We need that one. Yeah, okay, so I can't delete that one. How about this one? Oh, we needed that one. Do I need 0 mol? Nope. Do I need 0 div? No goal. Okay, so this is a way to sort of clean up what you're looking at here. Oh, again, if you want to do that manually, I suppose we might even suggest this. I'm not sure if it's possible to do this in an automated fashion. Maybe people should clean up the, add something to the ASAP tactic to remove things we don't need afterwards. Do we need nat cast of nat? No, we don't. We don't need that either. Anyways, so one can do that. You can also suppress this all. So if you don't want your final code to have all of this messiness, you don't need to use ASAP question. You can just use ASAP, and it solves it. So you get no goals with just ASAP in the first place. Or you can just do simp in this case. You don't need to put the question mark. If you put question mark, you can go and, again, find all the things that it thinks it should find. But you can also just put simp in here, and the final proof is a lot cleaner than the original one. But I suspect the speed of execution, or the number of heartbeats for the simp that has simp only, and then the hypotheses that it needs, will be more efficient than just the simp. But there's a pro and con between longer proofs that are harder to understand versus simpler proofs that take longer to calculate but are ultimately easier to read. Up here, I think these are not super long. I mean, if you only have 3 things in here, that's not a big deal at all. But once you have 3 lines of hypotheses, maybe you at that point say, that's awkward to look at. I don't want to read all that. And yeah, and then the power here, coming back to this, how might this be used as you build large networks of software? Because so starting next time, we're going to be talking about using a function of force to calculate things. Okay, so I want to do simulations with my force and my energy functions, but then on the side, I want to have proofs about my force and my energy functions. And if I can prove that these things are true, then I have confidence that I didn't make any mistakes in my force and energy functions. And that this proof holds for all values of real numbers, k, x, eq, and x. It's way more covering the possible cases than we would have if we were just doing unit testing. Okay, and one more question that we have coming from the last point of this slide. Deriv does not map a function to a function. It maps a function and a real to a real. Up thread, I was able to prove that deriv of function x of r to r squared is equal to function of x of r to 2 times x. Is that not mapping a function to a function? Oh, good question. Okay, so I'll post this text here. This is the question at hand. Okay, so we have, this was able to be proved. Deriv, I think actually this would be deriv. Oh, yeah, that's a good point. I should update this slide. I think you are very correct. Guest with username A. Okay. Yeah, you're right. This would be mapping a function to a function. Because well, deriv is taking a function, is being a function, is taking a function, and is producing a function. Yes. So this would be the same thing. Yep. Very good. My slide is incorrect. This is equivalent to, oh, thank you. I really appreciate that. You corrected me, and I will update those things. That's great. I'm glad we're fixing that. If for people who didn't watch until the very end, though, they might have the wrong idea. So mapping a function to a function is equivalent to mapping a function applied to R to R. Applied to something of type R to a real. Yeah, that's totally the same thing. Mapping n to a function is the same thing as the thing applied to the function mapping to the n. This is just one less step involved. So thank you. That's a great point to end on. Any more questions? Any more thoughts, discussions?